Hi, and welcome to our 8 a.m. press conference, The Melting Cryosphere. Our speakers this morning are Robert Kopp from Rutgers University, Daniel Fortier from the University of Montreal, Sabine Baumann from the Technical University of Munich, and Catherine Walker from NASA's Jet Propulsion Laboratory.
Good morning, and thank you for coming this morning. My name is Bob Kopp, and I'm a sea level researcher and director of the Institute of Earth, Ocean, and Atmospheric Sciences at Rutgers University. I'm going to be talking today primarily about a new study that will be out around 9 a.m. in Earth's future about the implications of our emerging understanding of Antarctica for global and local sea level rise projections and their use in decision making. So I'd like to ask you to start by considering two diverging roads. One road leading to 2 feet of global sea level rise by 2100, inundating areas currently home to about 100 million people. The other leading to 6 feet of global sea level rise, inundating the current homes of more than 150 million. Unfortunately, unlike the two roads shown on this slide, they aren't nicely labeled. The main study I'm going to talk about asks the questions, how can the evolving scientific knowledge about ice sheets shape estimates of how likely we are to end up on these or other possible roads? What are the implications of these global changes at a local level? And when will we be able to tell which one of these roads we're on? Our paper, the title of which is shown here, links together a widely used global and local sea level rise projection framework and a recent model of Antarctic ice sheet physics, and finds that thanks to potential instabilities in the Antarctic ice sheet, first of all, in a high emissions future, sea level rise could be considerably larger than estimated in the IPCC's fifth assessment report. But large-scale observations, such as global average sea level rise or continental scale ice sheet loss, won't be able to distinguish between a high road to 6 feet and a low road to 2 feet until the second half of the century. However, detailed local studies of ice sheet physics, some of which we may hear about later this morning, as well as improved geological reconstructions of past sea level change during warm periods, may help distinguish between these futures sooner. Nonetheless, meeting the Paris Agreement goal of net zero greenhouse gas emissions in the second half of this century would make 2 feet substantially more likely than 6 feet. To illustrate this, I'm going to show you a pair of sea level rise projections. The lines here show median, middle-of-the-road projections for a low emissions future consistent with the Paris Agreement, and down here, a medium emissions future, so perhaps most close to the one road we're currently on, and a high emissions future with continued growth of fossil fuels. These bars at the right show projections for 2100 that cover 9 and 10 simulations, so what we would call very likely. Global sea level rise projections consistent with the fifth assessment report of the IPCC indicate a very likely rise of about 30 to 80 centimeters, or about 1 to 2.5 feet, under low emissions, Paris consistent future, and about 50 to 120 centimeters, or 1.7 to 4 feet, in a high emissions future. But when we add in a model that accounts for potential instabilities in the Antarctic ice sheet, we get considerably different numbers at the high end. Instead of that 2 to 4 feet number, we find a very likely range of about 90 to 240 centimeters, or about 3 to 8 feet, under a high emission scenario. But we also find that these physics have little role to play under most projections in a low emissions future, which remains in the 1 to 3 foot range. The projection framework we've been using here is one that's been widely used in the United States for estimating the likelihood of different global and local sea level changes. And this slide here is showing you some of those reports, making use of this from places like California, Oregon, and Boston, among others. The ice sheet model we're using, which comes from work by Rob DeCanto and David Pollard, incorporates two important types of ice sheet instability. The first type of ice sheet instability, illustrated here, is marine ice sheet instability, which is better known. It's been studied for several decades, and some recent previous studies have found that it has the potential to contribute more than 30 centimeters, or about a foot, of global sea level rise over the course of the century. One of those studies is shown down there at the bottom. And we believe that this mode of instability may already be active in parts of western Antarctica, in particular in Thwaites and Pine Island glaciers, shown by some of those studies from a couple years ago there. The second mode of instability, which had not previously been incorporated into a continental ice sheet projection before that study listed down there at the bottom, is marine ice cliff instability, which occurs when massive ice cliffs with no protecting ice shelves can collapse structurally under their own weight. This photo here from Knut Christensen is showing you such an unprotected ice sheet edge in Helheim Glacier in southeastern Greenland. This mode of instability, or the potential for this mode, is currently observed only in limited regions, such as Helheim or Jakobshavn, but could become much more important going into the future. To illustrate the impacts of the difference among these scenarios, we worked with our co-authors at Climate Central, produced this website. You can't possibly read the URL, but it's stakes, stakes.climatecentral.org, which illustrates the impacts of our median local sea level rise projections through interactive maps, showing both high and low emission scenarios and the old projections and the new projections, including this ice sheet physics. And so I'm going to just click through an example for Norfolk, Virginia. So here, Norfolk at the end of the century, under a low emissions future, under the old IPCC consistent projections leading to about 70 centimeters of global sea level rise, and the new projections, little changed, about 80 centimeters of global sea level rise. 80 centimeters, excuse me, of local sea level rise. Here, clicking through, this is high emissions under the old projection, about a meter of local sea level rise. And under the new projections incorporating the physical model with marine ice sheet and marine ice cliff instability, about 1.8 meters of global sea level rise. So there is a potential for a very significant effect here. I want to also briefly highlight another paper related out today in Environmental Research Letters looking at the difference among different Paris targets, which finds that even among low emissions future, there is significant variability. For example, a 1.5 degrees Celsius future, the lower of the goals in the Paris Agreement, experiences almost half a foot less global sea level rise than a 2 degrees C future over the course of the century, and has a reduction in the peak rate of rise that is lower by more than the entire rate of rise over the last century. So in short, in a high emission future, sea level rise could be considerably larger than the IPCC's fifth assessment report. But large-scale measurements, like global average sea level, may not be able to distinguish whether we are on a low road or a high road until after 2050. Nonetheless, meeting the Paris Agreement emissions goal would make 2 feet much more likely than 6 feet. And even among the goals in the Paris Agreement, between 1.5 and 2 degrees C, there are some significant differences. These point to the need for both detailed studies of local ice sheet physics, which may help us distinguish between these past future by improving our understanding of the fundamental physics, and better reconstructions of past warm periods against which to test them. But for the moment, the current challenges posed by the instability of the Antarctic ice sheet, particularly in high emissions future, and the instability of our understanding of it, imply the need for flexible and robust adaptation strategies that account for this uncertainty as we plan for adaptation decisions in 2050 and beyond. Thank you.
Good morning, everybody. My name is Daniel Fortier. I'm a research professor at the University of Montreal and director of GeoCryo Lab. And today I'm going to talk about permafrost that is on the road in the subarctic and the Arctic. Okay. In Alaska and in Canada, people are living on the cryosphere. And their economy, of course, and transportation rely on airstrip and roads that are built on permafrost. And this permafrost is usually ice-rich. Permafrost is an underground phenomena. As you know, it is not as evident as glaciers or sea ice. And what we're looking at right now is the network of roads and highway in northern British Columbia and Canada, Yukon, the new we have the new road that goes to the Arctic Ocean in the northern Canada, and the networks of roads in Alaska. And as you can see on the right, we have a lot of roads that are built on different types of permafrost. So continuous permafrost maybe is something like 80% of the surface, and we have isolated permafrost and sporadic permafrost. The Alaska Highway is the only terrestrial link between Alaska and the contiguous United States that cross through Canada. And this road is built on ice-rich permafrost for about a quarter of its length. What you're looking at right now on the right-hand side is a permafrost core. And so you can see there's a lot of ice in it. And when we let this ice melt, we say that the permafrost thaw, but the ice melt, you have about 50% of settlement per volume. What you're looking at on the left-hand side is what is massive ice. It is called an ice wedge. You have the scale for the shovel for scale, and it's quite close to the surface. So the road, the Alaska Highway, about a quarter of it, is built on that kind of permafrost, which is really ice-rich. A recent study by a colleague of mine, Fabrice Calmels, demonstrated that this highway is highly vulnerable to climate warming and permafrost thaw. So it is indicated by the red color there, and we have all the segments, different segments that crosses different terrain units, different type of ground in Alaska and Canada. And on the bottom of the image, you have a picture of what it is before. We can see the road in the background, and once you melt these ice wedges in this case, you see that the road is starting to collapse. Of course, it is not really pleasant if you drive over that kind of road. And these are examples of permafrost damage, road damage that goes with permafrost degradation. So we have a lot of potholes. We do have it elsewhere than in permafrost areas, as you know. And we have important settlement and shorter cracking and some sinkholes as well. So this is a significant problem, and it affects now most of the highway. But today what I would like to present is the fact that, as you know, water will flow in the subsurface. There's a thin layer that we call the active layer that thaws every summer, and water will flow through it. And many of the road infrastructure will intercept this water flow. And as the water will flow under the road, it will help to melt the ice in the permafrost. So this is a simple sketch of what's happening. The permafrost starts to melt, and the water will travel underneath. And when water moves, it creates what we call convective heat transfer. So it is different than just atmospheric warming and the heat that goes through the ground. And this is up to 200 times faster than atmospheric warming. So this situation was not happening like 10 to 20 years ago because the permafrost was much colder, and actually the permafrost rose in the road embankment as they constructed it. And here, what I'm presenting is what the Russian called a talik. A talik is a permanent, if you want, unfrozen part of the ground in the permafrost. And so this is not a good news for roads. That means that instead of your road being built on frozen ground, it rests now on ground that is thawed and with a lot of water. So this is not some modeling. This is what we have measured since 2009, and this is new for this area. If you look at the 0C isotherm, so we have the depth on the left-hand side, and we have the dates there, the years, and then we have the temperature. So you can see there that the 0C isotherm is propagating under this highway. And when this happens, we have permanently unfrozen ground, we cannot refreeze it back. So the road will be basically floating on saturated ground, and it will subside and creates those cracks, potholes, and sinkholes. This is numerical modeling, and I'm sorry, it's a bit complicated to look at. We still have the depth there, and we have the years from 0 to 40 years ahead of us. So we're trying to look if we build a road, like the newly built road that goes to the Arctic Ocean in Northwest Territories, if we build new roads, what will happen when they intercept water? So on the upper part, you can see in the white, it represents a talic. So in about 15 years, most of these new roads will have talics. And those roads that were constructed, like the Alaska Highway in the 40s, already have in some areas these talic. And in the embankment, the slope of the embankment, we also have talic. It will take maybe a little bit longer, but in 15 to 25 years, we expect that most of the roads built on ice-rich permafrost in discontinuous permafrost that is a little bit warmer, let's say close to 0 C, will have permanently unfrozen zone underneath. So to sum up, the roads that are built on ice-rich permafrost are in general highly vulnerable to climate warming. And the degradation of permafrost really threatens the stability of roads and of course the security of drivers. The current climate warming will increase permafrost degradation just by atmospheric warming, and we expect as well that the hydrological cycle, I mean the subsurface flow, will increase as well. And then because it is a mode of heat transfer that is much potent than conductive heat transfer, it will probably increase. So we're having a positive feedback effect to permafrost degradation. The maintenance cost of these roads are already pretty high, and it will increase. And the roads that are built on, that are now on highly degraded permafrost or talic will need to be relocalized at very high cost. It's about $4 million a kilometer to build a road compared to non-permafrost areas under $1 million per kilometer. And of course, this will affect the economy of these areas. Thank you.
So, good morning, everyone. My name is Sabine Baumann. I'm from the Technical University of Munich in Germany. And I stayed at the Victoria University of Wellington as a visiting researcher last year. And I want to introduce my co-authors of this project that are Brian Anderson and Andrew McIntosh from the Victoria University of Wellington, Andrew Laurie from NIVA, Trevor Chin, who is working since 40 years on glaciers in New Zealand, and Catherine Collier, Wolfgang Reck, and Heather Purdy from the University of Canterbury. So in New Zealand, we have glaciers on the North Island and on the South Island. Here on the North Island, you can see this little red spot up here, and then here on the South Island, they are stretching over the whole southern Alps of New Zealand. And what you can see here are glacier areas from 1978 in red and in light blue from 2009. These data are coming from the GLIMS database. GLIMS is the Global Land Ice Measurements from Space initiative, and they have a glacier database with a global coverage, and in this database, multi-year layers are stored. And we have one complete glacier inventory of New Zealand that you can see here from 1978, and it was updated only for a small part. So what you see here doesn't mean that the glaciers reduced just to this small area, but the update was just made for this area because this is the central part of the Southern Alps, including well-known glaciers, and therefore they just took out this part. So we have one complete layer and one which covers about, let's say, 30%. So if you compare this area to other areas in the world where you have layers of maybe 10 time steps, there's a real need to update the inventory to get more years, more year layers, and also the date. It dates from 1978, so an inventory should be updated every 5 to 10 years. So it's really out of time, and an update is urgently needed. So that's what we did. In our project, we mapped the glacier area in two ways. So one part is the clean or bare ice glacier area, and the other part is a debris-covered glacier ice area. And debris-covered means that the glacier ice is buried under stones or gravel and looks like rocks when you look at it from space, for example, or also if you're there in the field, you won't recognize it as a glacier if you don't know. And what you can see here on the image are clean ice glacier areas in blue and the debris-covered areas in brown. And in sum, we have a glacier area of 857 square kilometers. If we compare our results with the old inventory, then you can see that the glacier area was about 1,240 square kilometers in 1978, so we have a change of about 31%, and also the debris cover reduced by 36%. The number of glaciers, reduced only a little bit, so that's a reduction of 3%. And what is quite important here is that the minimum altitude rose, so that is very common for all glacier areas, that the glacier tongue receded back, and this recession are about 80 meters in altitude, from 298 meters above sea level to 384 meters above sea level, and that's a change of 29%. The maximum glacier altitude, so the top of the glaciers, didn't change much. So if we take a look at the changes in the mean altitude, they come mostly from the lower parts of the glacier, because also the geometry of a glacier changes if the glacier tongue is receding. And so there we have also a change of about 80 meters in altitude, and that makes a 4% change. If we take a look at the change of glacier area per year, that are minus 0.8% per year. This is a closer look into our glacier inventory. What you can see here in the north, that is the quite well-known Franz Joseph Glacier with a little debris cover here in brown, Fox Glacier also with debris cover here, and the Tasman Glacier, that is a real large debris-covered glacier where several glaciers flow into the main trunk. In red, you can see the glacier outlines from 1978, and what you can see quite nicely, the picture behind is a Sentinel image, Sentinel-2 image, that here in this lower parts where the glaciers receded, they formed glacial lakes here, at this glacier here, and also up here. So when the glaciers recede, glacial lakes formed new or increased at several locations. How did we compile our inventory? The first complete inventory was based on orthophotos and geodetic maps, and we used remote sensing data that is mainly based on Landsat 8 and Sentinel-2 images. We had a semi-automatic mapping that is based on Landsat 8. What you can see is that in red again, that's the glacier area of 1978, and our satellite images cover the whole area. We didn't use the Sentinel images for this mapping because they were more heavily cloud covered, and so they were just used for post-processing purposes. And all these data are from the year 2016. That was a very negative year for the glaciers in New Zealand but if glacier mass balances are quite negative, it's quite good for making an inventory because you don't have a lot of snow fields staying along the borders of the glaciers. And pictures are taken from February and March, that is autumn on the southern hemisphere, and it's at the end of the ablation season where the snow cover is also at its minimum stage. So this is just a short description of the two satellite types we used. You can see here in the red box highlighted Landsat 8 and Sentinel-2, and they are quite recent satellites, and what is important for our mapping is here the radiometric resolution. Both have a radiometric resolution of 12-bit, and with this better resolution compared to older Landsat satellites, you get more information out of shadowed areas, and the pixels are not saturated so fast. So in summary, the last complete inventory dates from the late 70s. Our inventory is based on Landsat 8 and Sentinel-2 and dates now from 2016. We mapped a glacier area of 857 square kilometers with a 10% debris cover. The glacier area reduced by 31% compared to the old inventory. The minimum and the mean glacier altitude rose, and glacial lakes increased or formed new. Thank you.
Oh gosh, okay. Sorry, I'm getting over cold. Good morning, my name is Catherine Walker. I'm a NASA postdoctoral fellow at the Jet Propulsion Lab. And today I'm gonna bring us back to Antarctica and talk a little bit about new sort of local observations that we've been making, sort of what Robert referred to in his first talk this morning. So I'd like to acknowledge my two co-authors, Alex Gardner and Johan Nilsson. They did a lot of the data processing that I used to sort of bring this science story together. So these are some just little videos to show three different things about Antarctica that are important to know. Up on the upper left, the swirling in every one of these is the Antarctic circumpolar current. So that's the big current belt of ocean water that's going around Antarctica. On the upper left, that is the bed map. So if you took all the ice off of Antarctica, that's what the land below it looks like. So everything that's blue, that's not moving, that's blue in that photo, is below sea level. So it's grounded below sea level, sort of like here in New Orleans, or we're at sea level here, but everything in white in that image is above sea level, so I sort of whited it out because it doesn't matter to what we're talking about today. In the middle, those are Antarctic ice velocities, so you can see how the big ice shelves are the big sort of faster moving ones, the purplish color. And they're, excuse me, there are sort of rivers of ice flowing towards the margins of the ice sheet, and those are where you get those sort of ice cliff and marine ice sheet instabilities. Thank you so much. Thank you. And on the lower right, that is data showing elevation change of the surface of the ice. So you can see on West Antarctica, which is that way, hard to tell in Antarctica, everything's north basically, but West Antarctica is that way with the peninsula on it, and most of that ice is the stuff that's moving, that is losing more mass, losing more elevation. On East Antarctica, you can see a couple of red spots, which means its lower surface is lowering. But most of East Antarctica is pretty stable at this point anyway. So it doesn't really show up in many studies because it doesn't move very quickly and it doesn't lose mass very quickly. So this is just showing sort of ocean heat around Antarctica to sort of explain why it looks like it did in that last plot. These are estimated seafloor temperatures around Antarctica, and as you can see on West Antarctica, again, seafloor temperatures are at about 1 degree Celsius, which seems pretty chilly, but it's actually warm. And on East Antarctica, around most of the rest of the continent, the sea floor temperatures, at least on the continental shelf, are about minus 2.5 degrees Celsius. So you have sort of this insulating cold water sitting around most of East Antarctica, so you don't get much melting of the ice there. So just to refer to what I was calling out in my title, the Sleeping Giant Glacier has been referred to for a little nickname for Totten Glacier, which is in East Antarctica, and was one of those red spots that you could see on that elevation change map. I've circled it or squared it there. It's about 65 kilometers long, 30 kilometers wide. Not that I don't know if that means anything, but it's the biggest one in East Antarctica. And if the whole thing drained into the ocean, it would change sea level around the world by 3.5 meters. So that's pretty significant. And you can see in the lower right there, that's sort of a map from Greenbaum's paper a few years ago that shows sort of the amount of ice that can drain through that little sort of ice plug on the end. So it was observed to accelerate between 2000 and 2007, and then it sort of was slow, bumped up, and then after 2008 it's been stable but moving faster than it used to. So they just recently, past couple of years, people have been looking into why, and finally a ship could get in there because there was low sea ice that year in 2015, I think, and they could get a ship to measure sort of ocean water around there finally. And they could see that there was this warm water mass that had moved up onto the continental shelf and underneath the ice shelf that's sitting right in front of it. And then just recently, I think it was 2 weeks ago, there was a paper that showed that those changes in glacier velocity could be correlated with wind-driven upwelling. So it happens this way all around the world, but specifically in this sector, when you get an uptick in westerly winds, which are common there anyway, when they get more intense, you can think of it as they blow the top layer of water off, so warm water has to rise to sort of replace that water. So you get this warm water upwelling, and it floods onto the continental shelf and gets under these ice shelves. Not commonly thought to happen in East Antarctica, but they just found it. So finally, my work this year, we moved just west of Totten Glacier, so I've moved the box. And there's 4 smaller glaciers. They're named Underwood, Bond, Adams, and Vanderford. I've sort of highlighted them there from a Landsat image. So no one's really looked at these before because Totten Glacier sort of has a huge signal with respect to the rest of East Antarctica, so it sort of drowns everything out. But we have 2 new data sets that we've been using. So the velocities that I showed you are derived from Landsat images, and Landsat is very high, good resolution enough to be able to sort of track velocities through time. So before now, Antarctic velocities have been sort of based on snapshots in time. So we had one snapshot from like 2008 that everyone just looked at all the time. But now Alex Gardner and his group have developed this way of sort of getting that from Landsat so we can have a yearly basis for how fast things are moving. So then we can actually look at how velocities have changed. So looking at those, I'll show you in a minute, we've been able to see that these 4 glaciers in particular have been speeding up in the past 5 years or so. And then just again showing that bed map, showing what is below sea level in Antarctica on the lower left, zoomed in a little bit, that where these glaciers are draining in, Totten Glacier, they both drain the Aurora subglacial basin, which is that big sort of blue patch. And that would be home to something like the marine ice sheet instability that Robert talked about earlier, where basically as you get further and further inland, it goes deeper and deeper down. So if you can get water in there, it just easily sort of spills back and back until everything's melted. So that's a site for one of those occurrences. This got cut off a little bit. I'm disappointed by my PDF creator, but this shows, this is records from the Cryosat satellite, which is an ESA satellite. It's a radar altimeter, so it measures how fast the surface is changing. On the right, you have sort of a spatial image of that, so you can see where it's red, it's losing mass. So over those glaciers that I just had in the previous slide, you can see that most of those are red, so it's sinking at about, or losing elevation at about 0.3 meters a year. And it doesn't seem like a big deal, but as you can see from 2011 to just last year, It's basically gone from above zero, so not losing mass, to starting, and that's a monthly plot, so you can sort of see how monthly it's changed, and it's just on a downward trend, rebounding a little bit in the end of the year. And then these are the velocities I was talking about. So I've laid a velocity map sort of over those glaciers, and we can pick out along those profiles how fast the glaciers are moving since 2007 about. More data will be available later, but this is what's available now. So we can just look at the last 10 years, and that's sort of a busy plot, but what you can take away from that is that mostly before 2011 or so, it was down at about 3,000 meters a year moving towards the ocean. And then now, in the past couple of years or so, it's up at about 3,150 meters a year, which means it's increased since about 2010, 2011, about 150 meters a year, which might not mean anything to you, but the fastest region of Antarctica is on the, fastest changing, I should say, region of Antarctica is over on the West Antarctic Peninsula, and that changed in that same time period, changed about 500 meters a year. So this is about a fifth or a little less, or a little more of that total signal. So it's a pretty sizable signal for East Antarctica. So what we did was we looked at how that sort of, this is my last slide, how we looked at sort of why that was happening, if we could tie it to anything. We looked at a lot of parameters, but the one that tied best was when we actually looked at how ocean heat was changing in that region. So there's a little square around where I'm talking about, the bay right in front of these 4 glaciers. And then on the lower right here is a plot of how the total heat content, the total heat available in the ocean to melt ice, how that's changed since 1992. And what you can more or less see is that the total heat content available to melt ice in that region has risen since 1992. Those numbers don't probably really mean anything to you, but that's the general trend. And as you can see, it started going back down in the last year or so, so it's sort of correlates with the fact that it slowed down last year. But the point is that warm water is infiltrating not only the West Antarctic continental shelf, which has been known for a while, but we're starting to see that also happen on East Antarctica, on marine terminating ice, with not much floating ice, so you're going to start to see this ice sheet instability.
We'll now take questions from reporters in the room. Please state your name and affiliation.
This is Seth Borenstein of the Associated Press. For Catherine, just in terms of those 4 glaciers, and if you don't mind tossing Bond in there to making it the 5 glaciers.
Sure.
Well, first, for those 4, what kind of sea level rise footprint? I know Bond was 3.5. What if for those 4 smaller ones, what are we talking about?
So it's difficult to say without like a person that's more expert at predicting sea level rise from ice content, but those 4 glaciers drain the same catchment basin that Totten Glacier does. They're just sort of split around an island basically. So it's one big thing that's all flowing towards the ocean, and they go around an island. So Totten's getting most of it, and those are starting to move too, but they're both draining, or those 4 and Totten are draining the same exact area.
So what kind of time frame are we talking? I mean, I know that's even a big issue on the West Antarctic, but for example, for years we just have been hearing, don't worry, East Antarctic, don't worry about it. So what kind of time is this still, you're talking at a rate of 150 versus 500 in West. So I guess to try to put it for lay people, how, are we talking still centuries time frame? Are we talking decades time frame at noticeable sea level rise and actual just drainage?
So as far as East Antarctica goes, Robert can probably talk a little more to this than I can, but as far as East Antarctica goes, and at those speeds, and it's just concentrated right now anyway at that sort of location, it would be on the order of centuries. It's not, it's not immediate, but it is, once it starts happening, it'll be, it'll increase with time. But in terms of timing, it's not for a few centuries.
And finally, the one last one for me is, so why did this just start happening in the last, since 5-6 years, since 2011? What changed in this area, because it's still different than the rest of the East Antarctica, I mean, the winds you talked about earlier, those are, transitory. So there seems to be something else here. What is it that's just there and that just kicked in the last 7-8 years?
Well, some of it is just the ability, our ability to observe these things. So before this, we didn't have the ability to watch how velocities change. We've just had one snapshot or two. So we couldn't tell. We just sort of assumed they were staying the same through time. And with the advent of these new velocities, we can actually pick out these signals. Same with the cryosat mission. They've just enabled us to start watching this instead of sort of guessing or looking at images and figuring it's about the same. So some of it is that we can actually pick up the signal now. And it's getting larger, so you can sort of detect that a little easier. And some of it is the fact that ocean heat in general is increasing. It's getting warmer because oceans absorb sort of 90% of the heat on Earth. And so as temperatures go up, ocean heat goes up, and the Antarctic circumpolar current starts picking that up and bringing it around Antarctica. So yeah, it's just sort of a confluence of being able to detect that now, and then also just overall increasing heat.
So if I could add on to just from our modeling results, really Rob DeCanto and David Pollar's modeling results. For the East Antarctic under high emission scenario, depending on how strong this ice cliff mechanism is, we basically get a net contribution of anywhere between about 0 and 70 centimeters over the second half of this century, and then over the next over the next 3 centuries, between about 0 and 6 meters. So that's sort of the range. So if this ice cliff instability is quite strong, you could start seeing several tens of centimeters from the East Antarctic by the end of the century. But it's quite sensitive to how strong this mechanism turns out to be.
Are there any other questions from reporters in the room?
Hi, Kit Stoltz, Atlas Obscura for Daniel. Can you give us sort of a context for the Alaska Highway? It's a very long highway. It's very important to Alaska. How is it doing overall?
Yes. That's a long highway. It starts in the northern BC in Canada, where there's almost no permafrost. Then it arrives in the Yukon, and for a part, there's just a little bit of permafrost, so kind of fine for that. Eventually, from very close to the Alaskan border and then into Alaska, the permafrost is very ice-rich. For instance, there are some areas that were not glaciated during the last glaciation, and they develop the big, massive ice that can be like 15 meters high and 3 to 4 meters wide, and this is about a meter under the surface. So when you construct a road, you change the thermal regime, and the Alaska Highway is also a paved highway, so it's just picking up the heat, the atmospheric heat, transferring it down, and starts to degrade the permafrost. When you degrade ice-rich permafrost, it settles down, and so the road follows, so hence the cracks and the sinkholes and so on. But the important thing is that you put your embankment material lower down, so where you have the flow path. And embankment material is coarse, so you accelerate water flow. And water, even in this area, it's cold. If you go there for swimming, you will see it's cold, but it carries some heat. And as it flows, it will transfer the heat to the permafrost around. And then you accelerate the permafrost degradation. So right now, the Alaska Highway is really not in a good shape. And some areas will just need to be relocated. And this is very, very costly because you don't have just the cost of construction. You need to do the studies to find out where can we put that road where there's not a lot of ice. And in Yukon and Alaska, you have a lot of surficial deposits and not a lot of exposed bedrock. Bedrock is just the best for building roads. And back in the 40s and 50s, we like to build roads like we were building in the South. So we like a flat terrain, not a lot of curves, not a lot of up and down. These are sedimentary basins. So that's where the ice is. Basically, the Alaska is in probably one of the worst places that we could have put it if we thought about climate warming. And at the time, we were not into climate warming. Actually, the permafrost was rising in the embankment because it seeks equilibrium with the air. And now it's doing the opposite and everything is sinking. This is for the Alaska Highway, but there's numerous roads like that, and this is happening also in other roads. Mostly in discontinuous permafrost, where we have permafrost that is close to the point of thawing, but eventually it will also happen in continuous permafrost. So the roads going to Prudhoe Bay in Alaska, and the new road that was built a few weeks ago, that was opened a few weeks ago, going to the Arctic Ocean in Canada. And this is also affecting airstrips, so that the old transportation system is in bad shape, and of course buildings. Yeah.
Harvey Lyford, freelance. For Catherine and/or Robert, your slide showing the actual image of those 4 glaciers behind Tottenham, to me, glancing at it, it looked like one mass of ice, and I was wondering how you distinguish one glacier from another in that group. Do they flow to different places or what? And as a subsidiary question, is all of the ice in Antarctica attributed to one glacier or another, or does some just sit there and will never flow to the sea?
Those 4 glaciers, God, I'm having trouble this morning. Those 4 glaciers, I should have showed a little closer up of the sort of bedrock there. So glaciers generally, all of the ice in Antarctica flows basically from the middle, where you get a lot of snowfall, and everything's flowing out like a pancake. And so once you get to those margin areas, it sort of catches into deep spots, so little troughs or whatever, along the coast. So those 4 glaciers are each flowing along sort of a really deep trough around sort of topographic highs, I guess we should call them. And when you look at the velocity records, I should have showed it a little zoomed in, you can see that there's these rivers that flow into those valleys, and that's sort of how all of the ice in Antarctica eventually leaves the continent, and it flows out, catches in these streams, and goes out through these valleys. Yeah.
Okay, are there any other questions? Make me run. No, I'm kidding.
Hi, Brian Kahn, Earther. This is a question for Bob. I'm kind of curious, you used the DeCanto model. I'm curious to know if you could just talk a little bit about why, and I guess generally, if your perception or for anyone else in the panel, do you feel like that model is becoming more valuable, it's becoming more accurate, or why are you using it? What's the value in looking at those extreme scenarios?
Yeah, so the value of using it is that it includes some physical mechanisms that hadn't been in other models. There's still work going on the development of this model. So we're basically taking the model as it was when DeCanto and Pollard first came out last year. And the question we're asking is not, is this the best model? And in fact, we're looking at a broad range of parameters within that model, right? So as I said, for East Antarctica, it gives numbers from 0 to 60 centimeters and under RCP 8.5 for the end of the century, right? So we're looking at that space, and our questions are, well, if this is a reasonable, physically plausible model, what does that tell us about what's possible, and what does that imply for our ability to use knowledge about sea level rise projections beyond 2050, right? So we're using it as a tool that I think includes important processes that haven't previously been in other large-scale ice sheet models, which is why it's important, and using it to sort of understand what that does to our ability to make statements about projection. So its key value is that it includes these processes. It's evolving. There are other processes that aren't in any model that could change those numbers in either way. But I think what it shows us is what we still have left to learn.
Great. Well, we are out of time, so that concludes our press conference. Thank you very much. And next up, I think at 9 a.m. is Girls in STEM. Okay, thanks a lot.